Hi, I'm Mike Swanbom, and right now I'm going to solve one of the toughest alligator problems we've ever put on one of our engineering exams, and I hope you enjoy this. So for this problem, we have an alligator tank that is made out of glass, and it is set up with heating wire around the outside of the glass part, but inside of some insulation that keeps heat from escaping. The way the story goes on this problem is that Dr. Moeller turned this heater on and left it on accidentally without any water in it. And if he hadn't noticed, it could have caused a problem by making everything way too hot. But he did notice, and so he put some water in. And when he did that, the water essentially pulled some of the heat out of the glass. The temperatures equalized. The heater kept on pumping heat into the system for another 45 minutes, and it approached a equilibrium temperature at the end. And what our task is to use the information in this problem to determine how many wraps of wire we think, this heater wire, how many wraps of wire goes around the outside of the glass part of this tank. So this is what we're going to try to do. So the glass starts hot and gets cooler, the water starts cold, gets warmer. We then continue to pump heat into the system for 45 more minutes after we've added the water. So one thing that I'm going to mention here is that in some of our earlier versions of this class, we have dealt with an equation that relates resistivity of conductive material to the actual resistance of an electrical element that's made with that resistive material. And that is not really a part of our course in its current iteration. And so there's a portion of this problem, I guess I'll start off with this portion of the problem. It may not really make much sense to someone who's taking the course now because we don't really cover this part of it anymore. But I'll do that right here. So the resistivity equation the resistivity equation is that the resistance is equal to the resistivity, and sometimes we reuse some variables. This is the Greek variable rho, which is often used for resistivity. Sometimes we use it for density, but in this case we mean resistivity, times L over the cross-sectional area. So the idea with this is that you know the resistivity of the material, the length of the conductor, and the cross-sectional area of the conductor. You can calculate the resistance that comes out of that. Well, for us, we know, or we are given, the resistivity of this nichrome wire, and we're given a diameter for the nichrome wire. We just don't know the length. That's one of the things that's on the path toward finding the ultimate number of wraps of wire. And so what we're going to do with this is use a part of it and relate the resistance value that we have here to the amount of length of wire using the things that we do know. And the way that looks is that we have 1.5 times 10 to the minus 6th. It says ohm meters. Okay. If I take that and I divide it by the cross-sectional area of this wire, which we can express that with pi times the diameter. Up here we see the diameter is 1.9 millimeters. Okay, and we take that value and square it and divide by 4. That's just the formula for the area of a circle. We end up with some inconsistent units here between meters and millimeters, and so I'm going to fix that with a conversion from millimeters back to meters. And because it's squared, I need to square that conversion. Okay. Now I'm missing one last little thing. I've got rho and I've got A. I need to say that this is times however much length of wire that I have. Okay, so let me put these things in here. I have a fraction, 1.5 times 10 to the minus 6. Up there in the numerator. Down in the denominator I have another fraction where I have pi. I have 1.9, I need to multiply explicitly, 1.9 squared and divide by 4. Okay, and then the next thing I need to multiply by another fraction where it's basically 1 over 1,000, and I will square that. And what you see here, if we look at these units, and by the way, let me go ahead and store this, let me store this value I'll store it into m, because I'm going to probably need this value later. Let's look at the units of this real quick. We end up with millimeters squared, and that cancels out my millimeters down here. I have meters squared now in the denominator with meters in the numerator. And so what this tells me is that I end up with a certain number of ohms per meter, because I have a meter in the numerator and meters squared in the denominator. And so that value that I just had on my calculator, 0.529 or so, that is a number of ohms per meter of length of this wire. So let me put that in here. R is going to be equal to 0.529 ohms per meter times the length of the wire. Okay, that's something that we need to know in order to move on. And I'll make the mention, I'll make a comment here that if you're in an iteration of this course where you are no longer covering the resistivity equation, you might be given for a problem like this, rather than being given the information about the wire, the diameter, and the resistivity, you might just be directly given an amount of ohms per length for a type of wire, in which case you should be able to move on from here, in the same way that you would have in the previous iterations of the course. All right, so because I want to keep this in mind, I'll just actually move it up here. And let me get rid of the rest of this. All right, so the next part of this problem is to think about the energy balances. And this part isn't really that hard. It's like many of the other problems we've done. The change in energy for the glass plus the change in thermal energy for the water is going to be equal to the change in thermal energy overall. Okay, the change in energy of the glass happens because the glass is actually going to decrease in temperature from its initial temperature. The water is going to increase in temperature from its initial temperature, and the overall amount of change that happens will be due to the electrical energy that is introduced. All right, so and I'll remind us here, the equation we have for thermal energy, mass times the specific heat times our change in temperature, is equal to the change in thermal energy. Okay, we'll keep that in mind. We'll also keep in mind that electrical energy can be expressed in a number of different ways, but it's basically power times time. Some ways we've sometimes expressed that as V times I times T. In our case, we're probably wanting to relate this to the voltage here that's given and a resistance value. And if we remember another expression for power, instead of V times I, we can use a V squared over R times T. And this is an expression of how much electrical energy has been introduced into the system. All right, so let me do this. Let me put in our governing equation that's going to need to be solved in order to determine the amount of resistance that we need for our resistance heater. You see there, that resistance that we need is the thing we're trying to solve for. We have all the information we need to know the change in energy of the glass, change in energy of the water. We also have all the other parameters that we need for our electrical stuff. And so, you know, R is the thing that we don't know. We can find R by using this expression that I just came up with up here. Okay, let's write all that down. So, the mass of the glass times C sub P of the glass times the change in temperature, which I will write as the final temperature minus the initial temperature of the glass. And I only put one final temperature there because everything reaches equilibrium at the end of this problem. Okay, so that represents the change in energy. What I have here so far represents the change in energy of the glass. Now we're going to put in the change in energy of the water. So we'll need the mass of the water times the specific heat of the water times the change in temperature of the water, which will be the final temperature minus the initial temperature for the water. And then the last piece is the part where we have to handle the electrical energy that is added. And I mentioned, or I've kind of talked through that a little bit. We'll have the voltage squared over R, and R is really just, and I guess I'll put in one variable here because we haven't really defined a variable that describes this, but I'll just say 0.529 ohms per meter times L. And then this we multiply by time. Okay, so the most difficult thing, or maybe the most tedious thing I really should say about this problem, is coming up with how much mass we have for the glass and how much mass we have for the water. This is a little bit of a pain for this problem because we are given some geometry of this tank. We know the inside dimensions, they are given here. We also know that the thickness of the wall, that's actually given right here, this 2 centimeters. Okay, and so we need to figure out the volume of those materials and use it along with the density to figure out the mass. And I'll start doing that right here. So I guess we'll start with finding the volume of glass. Okay. And the way this works is I need to figure out what the volume of the outside of the glass tank is and subtract the volume of the inside of the glass tank. So the first thing I'll do is do that outside. And I'll just express it in terms of kind of the concepts here. Basically, I need the width. All right. And I'm figuring out the outside volume first, so I need to add to that 2 times the wall thickness. I take that and multiply it by the length, and add to that 2 times the wall thickness. And multiply this by the height. And what's tricky here is this has an open top, and so we're not going to add 2 times the thickness, we're just going to add 1 time the thickness. adding the thickness. And I need to take all of this and subtract. So what I have written so far is the outside volume, or it's the volume of if this was a big old solid chunk of glass, but we know that it's actually hollowed out on the inside, so I have to subtract the volume of the inside, which is a lot easier. It's just the width times the length times the height. All right, so let me start putting in values for all these things. So the volume of the glass is now going to be equal to, okay, the width is 2 meters plus 2 times the thickness, okay, and it says here the thickness is 2 centimeters. All right, 2 centimeters, I'll put that up here, 2 centimeters we can multiply by, there are 100 centimeters in a meter. All right, so this is 0.02 meters. Okay, so we're going to put in here 0.02 meters. That just will make this a little bit cleaner. Times the length of 3 meters plus 2 times the thickness times the height of 1.5 meters plus just 1 time the thickness. Okay, and then from this we will subtract the inside dimensions. So minus 2 meters times 3 meters times 1.5 meter. Okay, and so the volume of this glass is going to be, all right, so I'll try to fit this in here, 2 meters plus 2 times 0.02 times 3 plus 2 times 0.02 times 1 point, I need to put parentheses there, 1.5 plus 0.02. All right, all of that minus 2 times 3 times 1.5, which gives me 0.4264. And this would be in units of cubic meters. And because I might need to use that at some point, let me store it into A. All right, but we're not looking for volume of glass. We want to know what is the mass of the glass, because that's what we need to put into our equation up there. So the mass of the glass is fairly easy to find once we know the volume. It's the density of the glass times the volume of the glass. And the density of the glass is given up here, 2,800 kilograms per cubic meter. And we're going to take that and multiply it by the volume of the glass, which was 0.4264 cubic meters. Okay, so A times 2,800. That tells me that the mass of the glass is 1,194 kilograms. Okay, so that's the mass of the glass. Now we need to move on and figure out what is the mass of the water. Okay, this one's a little bit easier, but it's a similar process. So we're going to find the volume of the water first. Okay. Only thing that's a little bit tricky about this is that the water level is actually 10 centimeters down from the top of the tank. And so we're going to put in we're given the inside dimension, so that's good. And so we'll basically do 2 meters times 3 meters times 1.5 meters minus 10 centimeters. 10 centimeters is just 1/10 of a meter. And so our volume of water here is going to be 2 times 3 times 1.5 minus 0.1. Which is 8.4 cubic meters. And again, we don't want just the volume of the water, we want the mass of the water. And the mass of the water is just going to be equal to the volume of the water, 8.4 cubic meters, multiplied by the density of the water. And one expression for density of water is 1,000 kilograms per cubic meter. So this tells me that I will have 8,400 kilograms of water. All right, so those were a couple of the toughest things that we had to find, and we are now done with them. So let's actually get back to our main equation that we started with. Okay, we can plug in now the mass of the glass, which was 1194 kilograms. Okay, we can plug in the specific heat for the glass, which was 840 joules per kilogram degree C. We can plug in our final temperature. Everything reaches 21 degrees C, so I'll put in 21 degrees C. And we'll subtract the initial temperature of the glass, which we are taking to be that temperature that it reaches right before the water is added. So that would be the 88 degrees C. Okay. And to this we are going to add the mass of the water, which is 8,400 kilograms. Our familiar number that we're getting used to now is 4180 joules per kilogram degree C as far as the specific heat of the water. And then we'll multiply by the final temperature of the water, which is 21 degrees C, minus the initial temperature of the water, which is 19 degrees C. Okay, and we'll take all of that and we'll set it equal to our voltage squared. Okay, we have 220 volts. That'll be squared, divided by 0.529 ohms per meter, multiplied by L. That's what we're trying to find, is what's the length of wire that we need in order to get this resistance value that makes the proper heater. Okay, we'll multiply this by the amount of time that the heater runs. Okay, now if we look at this, what we end up with on the left side of this equation is going to be joules, because the kilograms cancel, the degrees C cancel, and the only thing we're left with is joules. What we have as this fraction right here is an expression for power, and then we have multiplied by time. This power, if we assume L is in meters, this power is going to come out in watts, and watts is joules per second. So if we want to make the time that we multiply by cancel the exact units that come out for watts, we need it to be in seconds, and so I'm going to multiply this by 60 seconds per minute. Okay, and that's a big messy equation, and ultimately what we want to solve for is L. Okay, so let's go ahead and stick all of this into our calculator. All right, what we have is 1194 times 840 times 21 minus 88 plus 8400 times 4180 times 21 minus 19. All right, so that's the left side of the equation. I get an equal sign in there, and on the right side of the equation I've got a fraction where I have 220 volts. That'll be squared. In the denominator, I believe I stored this value of 0.529 into M, so I'm going to recall that now and put in my M variable and multiply that by, here's the variable I want to solve for, and I'm going to use X for that variable. All right, then I'll multiply by 45, that's minutes, and so I need to multiply also by 60 from this over here. And after having done all this, hit shift solve. It wants to make sure that I still want this variable, or this value of 0.529 in my M variable. If you'd like to accept that, you can hit equals. Now we're going to solve for X, and it comes up with that we need 81.637 wraps of, or not, that's not wraps of wire, that's length of wire. Okay, so we'll put that in here, 81.638 we'll say. And that's in meters. We're getting very close, because now what we need to do is take this length of wire and use it with the perimeter of the tank to figure out a number of wraps. Okay, well, what's the perimeter of the tank? All right, I would say that we have two sides that are the inside dimension plus the thickness, and then another two sides that are the inside dimension, inside dimension plus 2 times the thickness, and then another dimension that is the inside dimension plus 2 times the thickness. Okay, let me real quick make sure I've got this. That's fine. All right, let me come up with this perimeter. The perimeter is going to be 2 meters plus 2 times the wall thickness. Okay, and I need 2 of those. To that, I need to add the other dimension, 3 meters, plus 2 times the wall thickness. I didn't fail to put one of my units in over here. And then this also needs to be multiplied by 2. Okay. So let's do this. We've got, I'll put my factor of 2 out front actually. 2 plus 2 times 0.02 plus 2 times 3 plus 2 times 0.02. That's that second part right there. And we'll hit equals. That tells me that I have, for 1 wrap of wire around the tank, the length will take 10.16 meters of resistive wire to do that. Okay, and so I'm going to slide this down real quick. And we'll do the last part of this problem, and it is that the number of wraps has to be equal to the total amount of length that we need, which was 81.638 meters. Divided by, what was this? 10.16 meters per wrap. Okay, so 81.638 divided by, and then 10.16 was the answer I just had. And so we are right about 8 wraps. And so the answer that I would pick would be F, 8 wraps. I hope that this has been a valuable problem to see worked. If it has been, then I would encourage you to hit like or comment about the problem and subscribe to my channel. Appreciate your watching this